nephron is the working bit of a kidney, and we learned that each nephron may have upwards of 1 million nephrons in it. Okay, so these are numerous microscopic little structures inside of the kidney. And what we learned is how the nephron works is the way it's built, because we know that what? Structure dictates function. Okay, so that's a really cool structure for a really cool function. And what the nephrons have to do is selectively sort off the volume of plasma so we can eventually form urine. And the way that it does is with this really cool vasculature in the nephron, where it's a little bit atypical, in that there's an extra set of arterial and an extra set of capillary that ensures that the nephron itself actually filters at one spot but does not allow for reabsorption at that same locality. So we can physically separate our blood plasma from the lipid filtrate. So let's go back. Let's look at that image in your handout. This image. I know it's already labeled, but we'll walk through it. The primary thing that we try to identify, or I try to point out to you guys, is that in the nephron, we're really following two fluids. We're following the blood plasma, and then we're following the filtrate once it's formed in two different kind of journeys. And therefore, we have different structures, our blood vessels and our tubes. Okay? Clearly, in the blood vessels, you have blood, and the tubes, we're going to have what we call filtrate. So let's just repeat our blood vessel structure. We said within a kidney, we know the renal artery brings blood to it, and those arteries will branch off, and eventually we'll get down to the cortex of the nephron, where a large artery will branch into an arteriole. And we named that arteriole. What is it called? The afferent arteriole. What does that mean? It's going away from the heart, but it's going towards the glomerulus. It's going towards the glomerulus, right at the nephron. The glomerulus is just a very specialized set of what? Capillaries. Where we'll elaborate more, but strictly only which process occurs here at the glomerular capillary. Filtration only. Today we'll elaborate why the pressure is so big that prevents any reabsorption. We'll look at anatomically what it is about the glomerulus. So we can form filtrates, and they can be trapped in the tubes initially by which tubular structure? The Bowman's capsule. I'll come back to the filtrate and the Bowman's capsule. Okay, so let's follow the blood journey. Well, as we said, enters the afferent arteriole. Filtrate can be formed with the glomerular capillaries. And then where's the next? Efferent arteriole. Not a venule, an arteriole. The efferent arteriole is carrying blood out of the glomerulus. So it's just a shunt. Then we can get into another typical set of capillaries. What's the next set of capillaries? Called paratubular, because they are round and adjacent to the tube. And you can see how around and interlaced the paratubular capillaries are around the tubes. Because it's the paratubular capillaries that are going to exchange content with the tubes and the interstitial fluid. Eventually, blood would then enter to a venule, then into a phase. What questions do you have about some of this blood supply within a nephron at this point? Yes. All of the purple, yes, in this image, all of the purple colored structures are the paratubular capillaries. So you can see how vast it encompasses the entire tube, hence the name paratubular capillaries. Any other questions or observations?
So the other capillaries are in the glomerulus. Do they have another name other than that?
They're either called the glomerulus or called the glomerular capillaries. Those are the only two names that I know of, but everything has about 10 different names, so. But those are the only two that I know. This what I'm using is the textbook use, and that's what will be on that.
That's all I get.
Additional questions or observations? All right, so we talked a little bit about the vasculature, and of course we'll get into our notes and elaborate a little more. But let's go back and review what we studied on Monday about the tubular structure. You guys noted that the tube actually originates surrounding the glomerular capillaries. Okay, it's called the Bowman's capsule. And it encapsulates, as the name implies, but it begins a tube. So fluid or filtrate actually gets transported. In a lot of these images, it's difficult to point out the obvious, that these are cells making up this structure. So it's not like a big plastic tube in your body or something like that. Individual little cells are making up this collective thing called the tube. And so, unit 1 material, right? Solubility, transporters, all that good stuff that goes into play as well with these cells as well. But they make a tubular structure, kind of analogous to like one of our vessels, okay, where blood plasma can go through. But here it's filtrate that's going to be pushed, right, down a pressure gradient. First into an area collectively called the what? Proximal convoluted tubule. What happens a whole bunch at the proximal convoluted tubule? Reabsorption. That means solutes are going out of the tube into the peritubular capillaries. So reabsorption implies the products are going back into the peritubular capillaries. So we can begin to reabsorb useful substances. Then the filtrate would go into the area called the descending limb of the loop of Henle, where we noted a high proportion of what is reabsorbed here. We noted that the descending limb reabsorbs a lot of water. High proportion. Okay. The filtrate is then pushed to the ascending limb of the loop of Henle, where there's a greater proportion of what? Salts. Okay, like sodium chloride is reabsorbed at a high proportion here as well. And then filtrate would then enter into the what? The distal convoluted tubule, where there's still what going on? Still reabsorption, but we begin to see a higher proportion of what?
Secretion.
Something called, very good, secretion. Where products are moved from where? They're going back into the tubule of the distal area. So it's reverse of reabsorption. Products, waste products, or lipid soluble products, so you put back into the tubule. Do I understand that concept of secretion? The products are going back in? I don't know if it was this class or yesterday's class. We're like, well, what's the difference between filtration and secretion? Was it this class or yesterday's class? The difference between filtration and secretion here is that secretion at your kidney tubules is regulated specifically by the tubule cell. So something that is being secreted back into the filtrate may have originated in the interstitial fluid. It may have originated in the plasma, like the movement of the peritubular capillaries. But during secretion, the kidney tubules specifically, for example, secrete potassium by using potassium transporters. It's specifically defining what is going into the filtrate. Selecting what can be added back into the filtrate. So it's the kidney tubule cells that are inhabitants moving that specific products into the tubule. Filtration itself is implied that physical pressing out of the capillary. It's presuming that happens, and then secretion moves the product into the tubule. That help or confuse?
Sure.
Filtration is a process to illustrate only at the capillary. Secretion is a more regulated process after filtration. For something, the kidney tubule itself says, I want potassium out. Right? So hormonally, what hormone could do that? tubes, not at your capillary, to secrete it back into the blood, or back into the filter. But secretion moves products into the tube to get rid of excessive or waste products. The filtrate would then move from the distal convoluted tubule where secretion happens and then into the collecting duct. Can any more modification happen here at the collecting duct? A little bit, but not near the magnitude like we've seen through the rest of the tube. So we really don't want to call it urine until it gets to where? Into the, well, even before then, the renal pelvis. So after it gets out of the collecting duct, it's no longer modified, then we can call it urine. In the tubes, we call it filtrate. In our vessels, we call it, in our vessels, capillaries, arteries, we call it plasma, blood plasma. Just depending on where it's located, we can dictate the more proper term for it. So if it's in your vessels, whether it's the glomerulus or whatever, it's blood plasma. If it's been filtered out, we call it filtrate. If it's been processed, and reaches the renal pelvis, we call it urine. Whether it doesn't have to necessarily make it down to the bladder yet, we call it urine. All right, so basically we have covered the rest of the presentation by looking at this image. So let's just go back through so you can fill in your notes and hopefully make some additional connections. We've already identified the nephron originates at the glomerular capillaries and is surrounded by the Bowman's capsule, or you can call it the glomerular capsule. There's a suffix when you're looking at a capillary or a capsule is going to dictate you're looking at the blood supply or the tubular structure itself. And I believe we left off around here, somewhere around here on Monday. We showed a more simplified image without much of the vasculature shown, but certainly looking at the tubular component of the nephron. But the glomerulus is the capillaries as identified, and the capsule surrounds it, traps the filtrate. Well, yeah, we did talk a little bit about the blood supply, very briefly, I think. We talked about there's actually 2 capillary beds and 2 sets of arterioles in the nephron, which makes it unique. We also identified that afferent arteriole brings blood to the glomerulus, and the efferent arteriole drains blood from the glomerulus, and it actually leads it to the efferent arteriole takes blood to the what? Peritubular capillaries. The location of our nephrons, the filtering in the convoluted tubules is all in the cortex. And so in the renal cortex is where you'll find the convoluted portions and the glomerulus and the capsule. In the medulla, those little renal pyramids, is where you'll find the actual loops, the descending and the ascending limbs of the loop and Henle. And you'll notice that not all nephron loops have the exact same length. Some are really short, some are really long, and we'll identify that in just a moment. As well, we noted that because there are 2 arterioles, they're going to have some different functions. I briefly mentioned it already. But I tried to visually point out something for you guys in the animation on Monday, that the arterial diameter is not the same between the afferent and the efferent arterioles. The afferent arterioles have a larger diameter than the what? Than the efferent arterioles. Why is that? It creates a greater pressure. Where? In the glomerulus, the structure between them. The whole point of having an afferent arteriole larger in diameter than its draining structure, if the draining structure, the efferent arteriole diameter is less, it's going to create a back pressure. So this allows for the capillaries to not only have a high pressure to filter, but it's so high that the glomerular capillaries don't reabsorb. It's this is the kind of magic, if you will, about the nephron. This the magic. It's magical. Yes. It's called filtering. The whole point is, if those arterioles were, say, equivalent diameter, blood flow would just go through, maybe a little bit of filtration, not so much. Or if the efferent arteriole is larger in diameter, still very modest filtration, so renal failure basically. So we've got to make sure the efferent arteriole is a little bit smaller in diameter than the afferent, so the blood kind of gets congested, if you will. Not blocked or clotted or anything, but just high pressure, making sure we form filter. So it does allow for filtration, that our fluid solutes, not our red blood cells, not our big proteins. Our liquids and our solutes are forced through the little capillary pores at the glomerulus. And so I already identified the role of this. We learned that there is a diameter change. I'm going to look at the efferent arteriole description first. And so the whole point is to make sure the glomerular pressure is high enough at the glomerular capillaries to let them do their job, but then they have a normal function for the peritubular capillaries to make sure that pressure is not damaging to them. So these are more kind of like what we've learned already about a job of an arteriole. If we look at the description of the afferent arteriole, obviously they're bringing blood to the glomerulus, but what we're going to add to that is these are going to give us some intrinsic control. So make a note here. These give intrinsic control to the flow in the kidney, the blood flow in the kidney. Or as better identified here, it protects the glomerulus from blood pressure changes. The afferent arteriole is going to be sensitive to the blood pressure entering into it, and it's going to be responsive. Is something out of order maybe? That's what I was kind of setting up. Okay, I'll come back to it. I'll get to it. It's kind of out of order. Alright, so let me go back. I'll clarify this, but the statement I have here says the afferent arterioles, they are going to give us protection from fluctuation or pulsing in the blood pressure. The word that we're going to apply to it is it gives us intrinsic control. The arterioles are the sensing part of the kidney. The afferent arterioles monitor the blood pressures because we don't want to damage the what? Which ones? We do not want to damage the glomerular capillaries. We need to make sure the blood flow is continuous and nice and safe for the capillaries. And so we'll come back and look at that in a minute. And then as we look at the primary structure of the efferent arterioles, we already identified it gives that back pressure, so it can filter the glomerular capillaries, but it also does normal capillary stuff in that it makes sure the pressure is adequate for the subsequent peritubular capillaries. So two roles, really, if you look at the efferent arterioles. That image that I had does correspond with this text, so I apologize for this flow, I guess. Some of our nephrons are long, extend long into the medulla. Some extend not so far into the medulla. Those that extend deep into the medulla are called the Juxtamedullary Nephrons. They go in, they're adjacent to, they enter into the medulla. And the job of the Juxtamedullary Nephrons are the long ones, the ones that have the really long loop at Henle. Their job is to make sure there's a gradient We want a gradient so we can keep stuff moving. So the job of the juxtamedullary nephrons is to create an osmotic gradient throughout the kidney. We'll come back to that. The cortical nephrons, they're built the same, but their loop doesn't extend as deep into the medulla, and so they have less to do with the gradient, and their primary job is just filtering, creating filtrate and modifying the filtrate. But either way, the juxtamedullary nephrons can also form filtrate. So they help create the gradient, but they're nephrons. They work like we've been describing so far. I'm going to go back to the image. Oh, this one will work just fine. On the far left, without reading the labels, quick, look, which type of nephron do you think is on the left? Cortical, on the far right. Juxta something, medullary, because it's longer. It extends deeper into the medulla. And the way it works is going to make sure that interstitial fluid is more, the concentration increases the more deep we get into the medulla. So it allows for the filtrate to continue to flow and exchange. Another structure that allows for the regulation of the nephron itself is called the Juxtaglomerular Apparatus. So don't get hung up on the prefix juxta. The suffix is where you need a medullary, means medulla, the length of a cortex in the medulla. The Juxtaglomerular Apparatus must be next to the glomerulus. And it's just referring to the cells adjacent to the glomerulus that regulate what's going on in the nephron. In the juxtaglomerular apparatus, there's a set of smooth muscle cells, as I was kind of alluding to, that surround the afferent arteriole that act like mechanosensors, or baroreceptors. They monitor pressure changes. So they are some smooth muscle cells, and they do give mechanoreceptor. They basically determine if a blood vessel fills up, what do you think those smooth muscles will do? If they're just sensing. They'll do it. If I've got muscles on the outside of this vessel, with some multi-unit smooth muscle on the outside, if blood vessel fills up, what do you think those smooth muscle cells will do? They'll relax and stretch. Okay? And that tells us, oh, there's a lot of blood flow. Versus, if there's not so much blood flow, the muscles could constrict a little bit. That's all they're doing is they're monitoring the stretchiness or, I guess, relaxation of the afferent arteriole. They're just monitoring. As well, they have the ability to secrete our product called renin. We've been dancing around it all semester, and we'll hopefully get into it a little bit today. SA is the question here. The juxtaglomerular apparatus functions to influence total SA for filtration. What do you think that might stand for? Surface area. Yes, thank you. I didn't see it in there. So they do, we want to have a great surface area for filtration here. In the way that the juxtaglomerular apparatus works, it's going to help enhance filtration surface area as well. So it's monitoring, it's enhancing filtration. It also has renin secreting ability when our blood pressure changes. This image is going to help a lot more, I think. This is looking at cross-section of the glomerulus and the Bowman's capsule. We can see the tube. And this is going to be our blood supply. The question is, which is which? Arterial. So I just need to look at the what? The diameter. This one must be the afferent, this one is the efferent. And the juxtaglomerular apparatus is kind of this whole region right here. It's more than just the arterial. It's the smooth muscle cells that are sensing. You see how they're on the outside? This thing fills up with blood, stretches, or it's not so full, kind of recoil. Okay, so just monitoring what's going on. We also have cells that can produce renin, which is going to regulate our blood pressure by this hormonal cascade. So blood would enter in here, filter out, and then exit via the ether arterial. The filtrate is trapped by the Bowman's capsule, and it enters into the proximal column of the tubule. This image is a little bit nicer in that you can actually see individual cells are illustrated here, and they would have their own transporters, receptors, etc. So to make sure our filtrate is modified properly. Can you see the region which is called the Juxtaglomerular Apparatus? It's adjacent to the glomerulus. The sensing cells around the arterioles and the secreting cells adjacent to it. Questions at this point? Looking at that, you have maybe a better image to look at. We've already kind of walked through the phases of urine formation, and we already talked about the terminology difference between filtrate versus urine. Filtrate is basically modified blood plasma, where it's all of our lipid soluble and our small components, right? But we know that our large proteins and our red blood cells cannot be filtered out. Conversely, urine is the modified fluid that will be eliminated. So excessives or waste products will be in the urine. So the filtrate is going to be what forms the urine. But we can't just, it's not magical like filtrate urine. Okay, we've got to modify it. The sparkles. To summarize what we learned in the summary video on Monday, is that the three primary phases include filtration, reabsorption, and secretion. And these phases are summarized for you in this simple image, looking at the glomerulus, where which process happens. Filtration, any filtrate that's necessary can be reabsorbed, and the excessive products can be secreted. So what we're going to go through is look at each of these phases individually. We're going to add a little bit more detail than just the kind of overview. Am I good to move on? All right, so let's first look at, you can make a reference to figure 18.7. You'll give an analogous image to which I just showed a moment ago. Filtration, reabsorption, secretion. It also clarifies excretion. What would be excreted? Urine. What could be reabsorbed? That would be an example, but collectively we could call it the filtrate. Filtrate, including water, solute hormones, etc., can be reabsorbed, but what is excreted is urine. I'm not going to show this video. If I have time, I'll come back to it. Again, this is going to seem a little bit redundant. We'll add some new terminology about the role of filtration. And at the glomerular capillaries, their job is to filter, obviously, they're capillaries. But they filter even better than the rest of the capillaries in your body due to the way that they're built. One, the blood pressure in the glomerulus is extremely greater than that in any other capillary. It's a huge pressure gradient forcing out blood plasma to form our filtrate. So therefore, it's going to have a total, what we'll call net filtration pressure is completely different. As well, we know our proteins aren't filtered. And if you look at the anatomy of the glomerular capillaries compared to capillary in your brain or your muscles or whatever, the glomerular capillaries will be a lot more, it's considered to be permeable. They're going to let more substances pass compared to capillaries elsewhere in the body. And so on top of or surrounding the glomerular capillaries is an area called the filtration membrane. So it's going to some cells that help increase surface area for our filtration. And so it's just a physical set of cells surrounding the glomerular capillary. And so it just facilitates, enhances filtration, as this kind of description implies. And if you look at this image now, it illustrates for you not only capillaries, but can you see the kind of beigey looking cells? They help form what's called the filtration membrane. And the way that these cells join to a capillary, okay, it gives it stability because it is high pressure, so it doesn't bust, but also it just enhances filtration by these, called these little filtration slits. And so filtrate can be permeated where these little slits are located. So we're keeping it strong, but letting, it's almost like the teeth on a comb or something like that. So a lot of fluid or filtrate can be passed between those slits, like plasma, out into the capillary. The rate at which a kidney or nephron, you can look at the whole kidney or both kidneys, is called the glomerular filtration rate, or the GFR. And this is just giving a rate of filtration, usually measured per minute. It's usually liters per minute is how you quantitate it. And it's dependent upon the total what? Surface area. Okay. So obviously if there's more surface area, we can have a greater filtration rate. The permeability of the membrane, so the more permeable, the greater the rate of filtration. And the total pressure in the glomerula. Okay, so these are not just pressure is what we're adding in there. How much surface area and how permeable are those glomerular capillaries is going to help illustrate the total or the glomerular filtration rate. Has anybody had blood work done recently and they give you your urea content? Has anybody had that recently? Out of the hospital? Maybe my blood. If you go get a blood profile, what's the proper word for that? Complete? Not a blood count, but metabolic? I think so. I think it's that one. Yeah, they'll give you your BUN, blood urea, and nitrogen. If you've had one of those recently, you can take the value of the BUN and you can go to that kidney.org website and plug it in, and it'll help you guesstimate what your filtration rate, your GFR, was when that sample was taken. So you can actually measure your total glomerular filtration rate. But you need something measurable to determine that. The rate of filtration, we look at what's called the net filtration pressure. Okay. How much filtration occurs is dependent upon the pressure gradient. Bigger the pressure, filtration rate goes up. Okay, so we just got some abbreviation here. The GFR, or the rate, is dependent upon the pressure gradient, or the net filtration pressure. If the filtration rate changes for some reason, it's probably due to a change in blood pressure. Probably not due to a change in surface area of your nephron. Probably not due to a change in permeability in the nephron. Those factors should be consistent. Okay? Your nephron should have a known structure. Right? It shouldn't change from today, tomorrow, whatever. It's a constant. Has a constant permeability, has a constant surface area for filtration. However, the blood pressure, you know, can fluctuate from moment to moment, as well as that can therefore influence your filtration at the nephron. So if I want to change the filtration rate, I need to change the what? The pressure at the glomerulus. Your textbook goes into more detail as far as applying terms, values, but I just want to look at this image for a moment to illustrate pressure isn't only outward, pressure is also what? Inward, which made sense to us when we studied capillaries and the rest of the body. We like that because it allows for reabsorption. But there's still an inward pressure at the glomerulus, but we need to overcome it. So So we need to make sure the glomerular pressure is not just high, it's really high, so that only filtration is pushed out. And so this is looking at the pushes and the pulls of the filtrate being formed, and it does have draws to be reabsorbed, so we've got to overcome that. So we look at the pressure and the osmotic, hydrostatic pressure of forces. If we pressure our blood out, okay, if we're outward moving, it's obviously the pressure is going to be higher in the capillary than in the bone capillary. But as we learned, if we add fluid here, the pressure would reverse. Okay, so we've got to try to overcome that. As well, if you remember from any old capillary, red blood cells and proteins are in there. We're separating fluids. Fluids, once they're pushed out, they're going to be inherently drawn back in because of the osmotic tendency of water. So the point is, the pressure has to be great in the capillary so that we overcome these inward opposing pressures at the glomerular capillaries. We do not want what? No reabsorption here at the glomerular capillaries. The total, right, the net filtration pressure at the glomerular capillaries is about 16 millimeters of mercury. At this point, doesn't mean much unless you look at it at any other capillary in the body, which has about 2 millimeters mercury pressure. Okay, so it's 8-fold pressure pushing the product out. Okay, so you can kind of see how that would be easy to reverse at a systemic capillary versus at the glomerular capillaries. A lot more difficult to reverse 60 millimeters versus 2. If we look at the blood flow to the kidneys, it's about 625 mils per minute. Okay, so about 6 liters per minute. Okay, so a little bit more than your total blood flow going to the kidneys. Of that, about 180 liters are actually filtered out per day. Okay, so we're eliminating, or I guess filtering a whole lot. Do you pee 180 liters? No. We filter about 100 liters a day. The bulk of it is reabsorbed. But we first have to have a high pressure to filter it out. If you look at any other systemic capillaries, the rest of your capillaries in the body receive about half of your total blood flow, or total volume, excuse me. So much less filtration, less pressure, etc., compared to the rest of the body. Which ties back into the statement we said that kidneys are reconditioning organs. So we can see they receive excessive amounts of blood flow. Sorry. All right. If we look at the filtration rate, it, just like anything else, needs to be maintained homeostatically. If our filtration rate is too high or too low, we're going to either overfilter or over-reabsorb, basically. So if my filtration rate is greater than necessary, so let's say I've got a systemic blood pressure problem, I'm not treating it, I'm not eating right, whatever, my blood pressure is high, my blood pressure in my kidney is going to subsequently be high. What's going to happen in that case? What? Won't be able to reabsorb. I'll filter really fast, but that blood plasma is being filtered so quickly, it's zooming through the capillaries, or zooming through the tubes, and reabsorption is going to happen properly. So you'll reabsorb some, but things that your body needs, like glucose or salt or whatever, hormones, where are they going? To the urine. It'll be wasted. Conversely, if your blood pressure is too low, you might filter, but will definitely reabsorb waste. Things that should be excreted from the body are no longer excreted. The kidney's not working. And so the kidneys have to be really sensitive. The nephrons have to be really responsive to blood pressure, so we don't foul up our filtration rate and we become toxic. It's more than our. And this is where I was setting you up a moment ago. Because the filtration rate must be precisely controlled, we have an intrinsic mechanism to regulate it. And if you remember early in the semester, intrinsic mechanisms are right there. We don't, even though we describe the nervous system as fast, it's faster because it's right there in the structure. And so the kidney themselves can regulate themselves intrinsically, or I think your book uses the term renal autoregulation, using that Juxtaglomerular Apparatus. But of course the kidney can be controlled extrinsically. Of course the nervous system can regulate. Of course the endocrine system can regulate it. Right? But it has a local, right, sensor, if you will. Hopefully it's becoming clear to you now how organs can be intrinsically versus extrinsically regulated. If we look at the intrinsic control in the kidney, there's two mechanisms to monitor it. One's called myogenic, and it's those smooth muscle cells around the afferent arteriole that respond to the blood pressure in the kidney itself, as well as monitoring the rate of blood flow through the Juxtaglomerular Apparatus. Not only just the rate, but also just physical sensors, the status of the vessels. One is called myogenic. Myo means what? Myo means muscle. Okay. The flow is talking about the rate of the blood through the structure. So, in other words, the nephrons are going to precisely regulate how much blood flow is going to enter or exit that structure. This simple image helps illustrate how the afferent arteriole, right, the status of it, can influence the activity at the glomerular capillaries. And so if our blood pressure is too high, the afferent arteriole should constrict a little bit, should control it there, and then hopefully bring our filtration back down to set point. Conversely, if my blood pressure drops, the cells can monitor it, and so the vessels, the afferent arteriole should, if my blood pressure drops, they should, yes, dilate. They said tighten, dilate a little bit to let more blood flow. If necessary, what else could we change? Yes, that's what we're changing here. Where else could we change resistance besides the afferent arteriole? The efferent arteriole. If necessary, we can change it, but the bulk of the control is going to come from the afferent arteriole. But we can certainly change the efferent arteriole if necessary. The nervous system we know should be the autonomic nervous system. If your fight or flight mechanism, should we filter more or less? Less. Rest and digest. Filtration should enhance. So we can see the dual innervation as well as opposite effects of one another, antagonistic effects of one another. So if your sympathetic nervous system is activated, the afferent arterioles constrict, shunts blood away from the kidney, because we know that we want to bring our blood pressure up and shunt the blood to your muscles and your brain, lungs, etc. Versus when your parasympathetic nervous system is in prevail, or I have here when your sympathetic nervous system is at rest. We want to put in parentheses in here. That implies the parasympathetic nervous system is going on. When you're resting and digesting, the kidney is going to be doing its own thing. So intrinsic regulation should be prevailing. When you're sleeping, you're sitting in class, or whatever, the kidney's monitoring itself, and it's sufficient enough to keep everything okay. However, when that fight or flight mechanism kicks in, we override renal autoregulation and constrict that afferent arteriole. Shunt the blood somewhere else. Don't form urine as quickly. They'll still work. We don't want to completely stop the blood flow to the kidneys, right? No, we don't want to do that. Shut down the kidneys. But we'll restrict the amount of urine that's being formed during that period of time. As well, we learned good old endocrine system can get involved with this as well. And so if we see the release of renin, so we see a change in blood pressure, renin can be released into the circulatory system. And it's going to initiate a cascade. It's kind of implied here. Once renin's available, we can take this inactive molecule called angiotensinogen. So just kind of roll over here. Angiotensinogen is in the blood plasma. The protein is inactive though. Only until renin's available can it then be converted into a precursor called angiotensin 1. This is an intermediate. It has to also be converted into something else. When a molecule called angiotensin converting enzyme converts it from form 1 to form 2. You may remember angiotensin 2 when we summarized blood pressure regulation in chapter 14. Is angiotensin 2 that's going to target the release of aldosterone. And what else? I mean, I really kind of played out on here. It releases aldosterone. What else? What did you say? ADH. And has an effect on our blood vessels to do what? Constrict. So when do you think we would see renin released then? When our systemic blood pressure is actually a little low for a period of time. Because if we constrict in our blood vessels and the rest of the body, our blood pressure goes up. Aldosterone promotes the release, or excuse me, what does aldosterone do? Promotes the, very good. I'm going to modify your terms, but you're correct. Reabsorption of sodium and secretion of potassium, which we said, we reabsorb sodium, we reabsorb water. Antidiuretic hormone directly also promotes water reabsorption. So we increase resistance and increase blood volume, so our blood pressure should go up. So, renin is released when the kidneys determine a decline in blood pressure over a period of time that it can't fix just by dilating the arterial. So they've got to call in some extra help. And it just promotes a blood cascade. Takes an inactive precursor, activates it. It can be activated into something functional, targets the adrenal cortex, the posterior pituitary blood vessels, all kinds of other areas in the body to collectively increase resistance and blood volume. To hopefully bring our blood pressure where? Back up to set point. We already noted, we talked through it. We said aldosterone is going to target the kidneys for sodium reabsorption. Chloride is going to follow it as well. And then water, which we know is going to bring our blood volume back up to set point. Hopefully. That's the goal anyway, to try to bring it back up to set point. This pathway is summarized for you in the image in your handout on the bottom of page 4. So I kind of summarized this. If our blood pressure drops, and the system is activated to bring our blood pressure back up. But if our blood pressure rises above set point, should we see this pathway activated? No. So the last sentence says if our blood pressure elevates, then we need a negative feedback, turn it off. And hopefully bring our blood pressure, maintain it at set point. Again, this is summarized for you in the image shown here as well as in your handout. You have a similar image, but I like this one. It's kind of visual, showing the organs in which the molecules are coming from or targeting. And so, which organ in your body makes this inactive angiotensinogen? The liver makes it, goes to the circulatory system, and it's just hanging around. It's not doing anything until what? So renin is released into the blood by the kidney. That is going to catalyze angiotensinogen into something called what? Angiotensin 1. It too is just an intermediate molecule. It also has to be activated by a molecule called angiotensin converting enzyme, or you could say ACE. It originates from where? The lung. Causing angiotensin 1 to be converted into angiotensin 2. Okay? Angiotensin 2 is now our activated molecule that can target multiple tissues, including the cortex of the adrenal gland to release aldosterone, which we learned promotes sodium reabsorption, potassium secretion, and also passively water reabsorption, which brings our blood volume up. What else does angiotensin 2 target? What other structure does it target? I don't know if it may target the heart, certainly the blood vessels there, and the rest of the blood vessels in the body besides just the heart. To do what? To constrict, increasing our resistance in our blood pressure. What else does it target? The what? The kidney tubules for sodium reabsorption, potassium secretion. The kidneys, the adrenal cortex, our blood vessels, and the somewhere in the brain called the probably does target the hypothalamus as well, but yes, hypothalamus and the hanging down below the hypothalamus that releases something. Posterior pituitary. Posterior pituitary to release, we said, ADH, antidiuretic hormone, or showed here called vasopressin. Okay, that comes from the what? Where I was trying to think? Posterior pituitary. But yes, the hypothalamus. And it does activate our thirst mechanism. So if you feel thirsty right now, your body is probably releasing at least angiotensin 2. The thirst mechanism is activated by, what did you say? So many things. It's like, it just wants you, your body wants you to drink water. Why? To increase your blood volume, bring your blood pressure up to that point. So when you're thirsty, the best thing for your body to take is what? Water. But we always go for, not always, but a lot of folks go for what? Coffee, Coke, sweet tea, whatever. But in those delivery mechanisms is water. I found it really cool, and you believe what you want to hear, right? You'll believe the evidence that supports your lifestyle or whatever, right? And if it opposes your lifestyle, you just think it's bad science, right? So I listened to an article on NPR earlier this semester, and they were talking about coffee drinkers. And you would think that if you drink coffee all the time, you would eventually become what? If you drink only coffee, you would think your body would well, you do become as well. And then going here though, you become dehydrated, right? But you're right, you become drug dependent. My drug of choice, caffeine. But there's some scientists who are studying people who are habitual coffee drinkers. And they were presuming, well, if you drink coffee all the time, you must be dehydrated all the time, your kidneys must not work. And the research found that those people who are now conditioned to drinking X number of cups of coffee a day, there's enough water in the coffee that their body is adapted, that they're still getting the fluid that they take, and the caffeine is not antagonizing. If you think about caffeine is described as a diuretic. And so with long-term exposure, like your regular coffee drinker, your body kind of adapts to that caffeine, and you don't become dehydrated from drinking too much coffee. And I'll be obviously, if that's all you drank only, okay? But there's just like people who drink their morning coffee and maybe afternoon coffee or something like that, who've been doing it for years. Their kidneys function just fine compared to those people who don't. Their water reabsorption, let me say it that way, is the same. The research that I studied was only coffee. I don't know that they looked at other drinks. Yeah, so our body's pretty awesome, right? And it'll adapt, it'll do what it... And that's a good point. I mean, drinking water has its obvious benefits, okay? It keeps your blood plasma osmolarity at set point. But despite what we do to our bodies are going to do their level best to keep factors in the set point. And so if you don't drink pure water, you do drink a lot of juice or whatever, those fluids do have water in them, but your output will be maybe more concentrated than someone who drinks only water. Okay, so the kidney would appropriately respond, taking what it needs, eliminating what it doesn't. All right, so extrinsic control, endocrine pathway, complex, but hopefully to review what we talked about, the pituitary and the adrenal cortex. I was just looking at getting it started by using this product from the kidney called Renin. Kind of kickstarts it. Okay, so where that led us is the first phase of urine formation is first it has to be filtered. Okay, and we said, well, what about the structure allows for filtration? We talked about the structure of the glomerulus, and the filtration rate can change. Now we're saying, well, once that filtrate is formed, what happens to it? We said the next major step is called reabsorption, and it's properly called tubular reabsorption. And it's just normal cell transport mechanisms, active, passive, secondary active, all of our active and passive transport mechanisms that we studied early in the semester apply here in the kidney cells as well. Some products that are ions, okay, can move between cells, like we saw in other capillaries. Okay, so we can move, reabsorb charged particles via what's called paracellular or between cells. So calcium, magnesium, potassium, whatever. Our organic nutrients like glucose and our other sugars and some of our amino acids, they are specifically pumped and transported using a transporter from the filtrate back into the kidney cell, and eventually from the kidney cell out in the interstitial fluid, and then across our peritubular capillary. So there's a lot, these molecules are really moving across a lot of cell membranes, basically. We already studied as well our water reabsorption, and our ion reabsorption can be extrinsically controlled by our hormones. So two that we focus only on include antidiuretic and aldosterone. Those two hormones are the ones which we study can change this reabsorption. If we look at a specific example of sodium, our good friend sodium-potassium pump is involved. And so if we look at the filtrate going in the tubes, the tubular cells on the side facing the lumen of the tube would have a sodium-potassium transporter. And it's going to selectively reabsorb sodium in one way, and the potassium in my directionality. Actually, it's on the cell, I think it's on the region facing the interstitial fluid. Pumping sodium from the cell in an interstitial fluid and the potassium back into the tubular cell. I'll show an image that will help a little bit better. What happens is, once these ions or other molecules are out of the tubular cell into the interstitial fluid, then our typical gradients, pressure, osmotic gradients, would move them back into the capillary. So there's a lot of pressures as well. The osmotic pressure, that draw of the peritubular capillaries, we noted that they've removed a lot of plasma, the high protein, high red blood cell content, so products are just going to be naturally just attracted back into the peritubular capillaries once they're out in the interstitial fluid. If we look at sodium, though, we're spending energy to reabsorb it. Once we spend energy to reabsorb it, it creates a gradient for a lot of other molecules like glucose, etc. So we get reabsorbed back into the blood. So it's okay to spend energy to reabsorb sodium, we kind of get a payload of additional molecules to be retained back into our peritubular capillaries. I'm going to come back to this text, but I just want to show this image. This is where I was getting hung up. This is zooming in, looking at, say, the proximal convoluted tubule region. This is looking at some tubular cells. Those are really microscopic. Up till now, we've just seen it as a straight line. So we're zooming in, looking at a few cells making the tube. They would obviously make a circular structure. The lumen would be hollow where our filtrate is flowing, and there would be another set of cells. I think here's just a cross section over here. The filtrate, high pressure is flowing through fast, and we're going to have gradients try to reabsorb certain substances. Sodium is going to be reabsorbed, and we're going to have some secondary active transport, which you guys talked about in the pre-lab, such as glucose and ions, etc. Just picking them out of the lumen of the tube and putting them into the tubular cell. You see how it's just going into the cytoplasm of the tubular cell? Once they're in there, we don't want to keep them in the tubular cell. We want to get them out. So we have to have another transport mechanism on the other side of the tubular cell. Does that make sense? Pull it out of the lumen, put it in the tubular cell, take it out of the tubular cell, put it in the interstitial fluid. So for example, the sodium-potassium pump on the capillary facing side will pump sodium out, but pump potassium in. We don't want to keep it in there, and so we just add a little what? A little channel. We'll pump it in, and it just allows for the continual cycling. So we're pumping more sodium out, and the potassium just kind of cycling through, maintaining a balance. Okay? Some obviously could be reabsorbed back into the circulatory system. Because of the structure of our capillary cells, sodium could go back into the plasma. That creates a gradient for, say, charged particles like chloride ions. Notice this is going between cells. What term did we use before? Paracellular. So that'll happen when we have this gradient established. Sodium, positively charged cells, chloride ions, water right through aquaporins. It's going to follow that gradient. And urea, although we said is a waste product, it's lipid soluble. We can't trap it anywhere. Okay, so even though we don't want it in our blood necessarily, it's going to diffuse at about 50-50. Half of it will stay in the tube, half of it's going to go into your circulatory system, which is why our kidneys need to work all the time, which is why someone who has kidney failure better go to their what? Dialysis regularly, because they're going to build up toxic products, including urea. So each dialysis treatment is going to remove how much of the urea? 50% of it. If they skip a treatment, it's just going to retain in the body. All right, so we learned as well water can osmose in. Our charged particles, can diffuse through channels. Lipid-soluble substances can diffuse across cell membranes. We already showed with the previous image that organic nutrients can be selectively transported across the cell membranes as well. So we filter, then we reabsorb, and the next, I'll skip ahead real quick. Next phase is what? I'm going to skip ahead to the next phase, which is secretion, which is nearly the reverse, where the tubular cells regulate what is put back into the lumen of the tube. This is specifically going to remove excessive products like potassium, urea, whatever substances can diffuse back into the lumen. So the question that we had on Monday is well, what's the purpose of it? Well, the purpose is we can get rid of substances that aren't already in the filtrate, like urea, that are lipid soluble, they're hanging around. Well, let's flood it back into the filtrate. We can we can secrete those substances. We can get rid of excessive products like potassium. You know this ion has to be homeostatically regulated, otherwise our muscles and our nerve cells, etc., will malfunction, which is not good. So we can specifically secrete potassium back then. And as well, it helps regulate our blood pH by removing excessive bicarbonate ions or excessive hydrogen ions in the form of hydroxide, whatever the case may be. So it can fix problems. Besides just blood pressure, blood volume, it can fix pH problems that maybe breathing patterns can't fix. And so long term, we can get rid of excessive bicarbonate or excessive whatever that your body might have. So there's multiple reasons why products would need to be secreted back into the filtrate. This image is trying to illustrate the secretion process, not as anatomically kind of detailed as the previous image, but we can certainly see the directionality. The setup is the same. So we have a peritubular capillary, interstitial fluid, tubular cell, and the lumen of the tube. Notice the directionality. We can see some sodium transporters. If we get more to the distal end of the tubes, notice where the potassium channels are located this time. The potassium channels are located where? Going into the lumen. At the proximal convoluted tubule, the potassium channels are going where? To the interstitial fluid. So just changing where the gate is, if you will, is going to influence whether something's reabsorbed or secreted. So tubular secretion is designed so that products can go back into the filtrate. And this one's very much regulated in this case. Your lipid-soluble substances would just diffuse down the gradient. We're basically out of time, and I think y'all got the purpose of the kidneys and how they work. With the primary processes of filtration, reabsorption, and secretion. I will not hold you accountable for how different concentrations of urine will be formed, whether a dilute versus a more concentrated urine are formed. But for your peace of mind, I'll go ahead and give you the balance of the handouts in a PDF document on D2L. But I won't hold you accountable for the differences of concentrated versus dilute urine. Your exam will be on Monday, 8 o'clock. So regular unit exam, pencil, brain, coffee. And again, I'll try to get those grades to you as soon as I can.